Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing with our study of carbohydrates, and we're going to move on from monosaccharides and take a look at disaccharides. Disaccharides are carbohydrates composed of two monosaccharide units. These units are joined together by what is called a glycosidic linkage. This is an ether linkage or a carbon-oxygen to carbon linkage. The typical glycosidic linkage is from the anomeric carbon of one monosaccharide unit to the fourth hydroxyl group of the second. If the anomeric carbon has an alpha linkage, then the linkage is often identified as an alpha 1,4. This can also be designated as a 1,4'-alpha glycosidic linkage. If the monosaccharide anomeric carbon has a beta hydroxyl group, then the connection in the disaccharide is referred to as a beta 1,4 or 1,4' beta glycosidic linkage. In this course, we'll use the alpha 1,4 and beta 1,4 designations. Now, these glycosidic linkages between two monosaccharide units can be hydrolyzed by hot dilute acid to form free monosaccharides. The most common disaccharides are maltose, cellobiose, lactose, and sucrose. And we're now going to take a close look at these four disaccharides. The first one is maltose. Maltose involves an alpha 1,4 linkage. Between two D-glucopyranoses. Here's one. D-glucopyranose. And you'll notice I've made the linkage off the anomeric carbon alpha. And I hook it to the second D-glucopyranose. And I'll make it, the OH still down, so I'll make it alpha. And this is how we can represent the Haworth. Now, just so you don't misunderstand the line formulas, these two positions here are not carbons. This is one bond to oxygen and another bond to oxygen. It just allows me to write it in a fairly linear fashion. In the disaccharide, we see that the alpha 1,4 glycosidic linkage, the anomeric carbon here, is a full acetal. That carbon has two singly bonded oxygens. There's no OH, so it's not hemi. And there's a hydrogen there. It's not shown because of the line formula, but we know there is a hydrogen there. It is hooked to the hydroxyl group, or what was the hydroxyl group, of the fourth carbon in the other sugar. Hence, this is an alpha 1,4 glycosidic linkage. Now, the other end, the other sugar, the other monosaccharide fragment, has a hemiacetal end. And like all hemiacetals in monosaccharides, the disaccharide hemiacetal can ring open. That is, I can place this molecule in equilibrium with the open chain form. Because one end can ring open, the molecule maltose is capable of mutarotation. And this mutarotation, a change of optical rotation, is caused by the one end alternating between an alpha at the anomeric hemiacetal end and a beta. And so we can draw a beta version of maltose. Now note, beta maltose still has the alpha 1,4 linkage. Nothing changes there. But it is the hemiacetal end that is now beta. So here we have alpha maltose and beta maltose. And they can interconvert through the open chain form. They are in equilibrium where the one end of the hemiacetal actually opens, forming the aldehyde. Notice the full acetal end stays closed. Notice the alpha 1,4 linkage stays intact. In order to be a maltose, I must have an alpha 1,4 linkage between the two D-glucopyranose monosaccharide fragments. Not only can the molecule mutarotate, but the molecule is also capable of being oxidized, and hence maltose is a reducing sugar. If I react this with Br2, H2O, pH 5 to 6, that aldehyde fragment will become a carboxylic acid. Now, that means with Tollen's reagent, which is in base, I would get a CO2 minus here. And it would stay like that. It would stay open. But with Br2H2O pH 5 to 6, we recall that we would produce gamma-lactones. Notice, however, in this case, let's use a different color, that the alpha carbon, beta carbon, the gamma carbon, the gamma carbon's oxygen is the one tied up in the alpha 1,4 linkage. That means it's not available for reaction or cyclization. That means a gamma-lactone can't form. If you can't form a gamma-lactone, you form a delta-lactone. That means this OH comes in and cyclizes. This OH will attack the CO2H. Now, it doesn't attack the aldehyde. Remember, this aldehyde becomes a double bond OH. And then the OH attacks that. And once that reaction's done and you've lost water, you will form a delta-lactone. Of course, we're running out of room. And so this is our delta-lactone. Okay, so there you have it. Maltose consists of two D-glucopyranoses linked together. Alpha maltose consists of two alpha D-glucopyranoses linked together. Maltose has an alpha-1,4 glycosidic linkage, but because one end's a hemiacetal, it can ring open, which means it's capable of mutarotation. That's the change in optical rotation. That is caused by the interconversion from the hemiacetal being alpha to a hemiacetal being beta. And so there are two forms of maltose, alpha maltose and beta maltose, but note both have an alpha-1,4 linkage. All right? Also, because there's an open chain form version, it is a reducing sugar, can get oxidized. In the case of Br2H2O, or if we used 1 Tollens reagent, 2, let's show you that, instead of Br2H2O, I could have written Tollens reagent. Now, Tollens reagent by itself would make a CO2 minus here, and that would stop. That would not do anything else. But if we happen to say step 2 in acid, H plus or H3O plus, then that means that becomes a CO2H after step 2, and then it will form the delta-lactone. So it is reducing sugar. Maltose is formed during the amylase catalyzed degradation of starch. Maltose is a key component disaccharide found in starch. The next carbohydrate we want to consider is, or disaccharide, is cellobiose. Cellobiose is identical to maltose in every way except one. Instead of an alpha-1,4 linkage, it has a beta-1,4 linkage. So I'm going to change this linkage here. We're going to draw it this way. So there's cellobiose, and let's correct this because it also has, and this one would be alpha cellobiose. Alpha cellobiose. Because it also has a hemiacetal end, it can ring open and interconvert to beta cellobiose. And in fact, just like alpha maltose was the repeating unit found in starch, beta cellobiose is a repeating unit found in cellulose. So everything that applied to maltose applies to alpha and beta cellobiose. It can ring open, it can interconvert between alpha and beta forms at the anomeric carbon, and it can be oxidized and hence is a reducing sugar. So everything occurs the same. Now, I'm going to show you with this beta cellobiose, I'm going to rub out its name for a second. The reason we draw it with these zigzags in the middle at the glycosidic linkage, and that linkage, you note, is beta 1,4. So it has a beta bracket 1 arrow 4 linkage. This beta 1,4 linkage, we draw it with a zigzag just so we can draw the molecule in a linear shape. If I was to draw it without the zigzag, you see the Howers take up a lot more space. These two drawings are the same thing. And so note that vertices of the zigzag are not carbons. They're just a bent bond so that we can write the molecule linearly without taking up too much space. So you should be comfortable with seeing the molecule either way. So right here, these two molecules are the same. So these positions are not carbons. What they are is just a single bond. Okay? Of course, you'll notice I missed some CH2OHs here. Can't believe I did that. And those should have been there in the case of maltose. So to reiterate, for cellobiose, we have a beta 1,4 glycosidic linkage. It's not broken. The full acetal end is not broken. Only the hemiacetal end can ring open. Hence, cellobiose, like maltose, can mutarotate. It's a reducing sugar. It can be oxidized to the delta-Lactone. Can't make the gamma because the gamma oxygen's tied up in the full acetal linkage. Cellobiose is repeating disaccharide unit found in cellulose. And if you partially hydrolyze cellulose, you get cellobiose. Okay. Well, this is getting a bit cluttered. Let's draw it all together one more time and take a look at lactose. Lactose is an interesting disaccharide. Unlike maltose or cellobiose, which has only one sugar for both ends of the disaccharide, lactose is made up of the combination of two sugars. The first one, which possesses the full acetal, is a beta-galactose. A beta-galactose. So we have this type of linkage. And that is hooked to either an alpha or beta D-glucopyranose. So we have a beta-galactopyranose, a beta-D-galactopyranose connected to an alpha or beta D-glucopyranose. And so we can start with a beta. Okay, so what do you see here? Well, this is our lactose. The galactose is connected through a beta 1,4 linkage. And it's connected to the 4th hydroxyl of a D-glucopyranose. So our beta D-galactopyranose is connected to the 4th hydroxyl group of a beta or alpha D-glucopyranose. Because the glucose has a hemiacetal end, it can ring open. And we can draw the ring open structure. And we might as well. So I can ring open. And from this ring open form, it can close again. It can go back to the beta form, or it can form the alpha. And so there is what we might call alpha lactose, and the upper one represents beta lactose. So beta lactose and alpha lactose are similar to alpha and beta cellobiose in that they have this beta 1,4 glycosidic linkage. The only difference between lactose and cellobiose is cellobiose is made up of 2 D-glucopyranoses, whereas lactose is made up of a galactose fragment and a glucose fragment. Now remember, it is very important that this be your galactose fragment. You can't reverse it and have the same sugar. It would be a completely different sugar if you switched the D-glucopyranose with the galactose. Now, because there is the free hemiacetal, which can ring open, it can mutarotate, so optic rotations will change, and that is caused by the equilibrium between the alpha and beta lactose. Likewise, we can make the delta-Lactone, and you can react the open chain aldehyde to make a carboxylic acid, which would give you the delta-Lactone. Lactose is commonly referred to as milk sugar. Now the last disaccharide we're going to look at is sucrose. Sucrose is different from the other three disaccharides. Sucrose, or table sugar as we know it, consists of two different monosaccharides. It consists of an alpha-D-glucopyranose so here is my D-glucopyranose. And that is connected to a beta-D fructofuranose. Now what this means is we've connected one anomeric carbon to the other anomeric carbon. The anomeric carbon of the glucopyranose is connected to the anomeric carbon of the fructofuranose through a glycosidic linkage. I guess this would have to be referred to as an alpha-beta 1-2 linkage, where we're connected via an alpha linkage from carbon 1 of the glucopyranose. This is carbon 1. Here's carbon 1, that's carbon 2. The anomeric carbon's carbon 2 in fructose because it's a ketose, and it's a beta. So an alpha-beta 1-2 linkage. Here we have a full acetal. Here we have a full ketal. There is no ring opening from full acetal and full ketals in aqueous solution. Hence, there's no mutarotation, and sucrose is not a reducing sugar. Now, table sugar is isolated from sugar beets, sugar cane, maple sugar. Sucrose can be hydrolyzed by the enzyme invertase. To both alpha-D-glucopyranose and beta-D fructofuranose. So this enzyme can cleave this linkage. Now both molecules can undergo mutarotation. So when the enzyme does this cleavage, you get a mixture of monosaccharides. You get 32% beta-D-glucopyranose, %, alpha-D-glucopyranose, and 34% beta-D fructofuranose, and 16% beta D fructofuranose. Now, during the conversion, the cleavage, during the process of mutarotation that generates these percentages of sugars, the specific rotation changes from an alpha of plus 66.5 degrees, and it changes to an alpha of minus 39.5 degrees. Essentially, the sign of the optical rotation from the initial cleavage in the hydrolysis to the final mixture has undergone a change of sign. The sign of the rotation is inverted. And so this sugar mixture, for which we get this inversion of optical rotation, is called invert sugar. Now, invert sugar tends to be less crystalline than sucrose due to the large mixture of constituent monosaccharides. Honey is made up mainly of invert sugar. When you have a lot of different structures and you try to crystallize them, and often it is possible to get a non-crystalline oily product. The difference in a crystalline sugar like sucrose and a syrupy sugar like honey, which is mainly invert sugar, has to do with the fact that sucrose is a single molecule, but invert sugar is made up of significant percentages of very similar yet distinct different molecules, and so it has difficulty crystallizing. Now, it's known that D plus glucose and D minus fructose are important constituents of sucrose, and historically D-glucose has been referred to as dextrose and D-fructose has been referred to as levulose. Sucrose was first synthesized in 1953 by Lemieux at the University of Alberta. So Alberta does have something to put it in the Hall of Fame with regards to synthetic chemistry. Now, what do we do, however, if, say, we have a molecule that is a disaccharide, but it is not one that has a common name. It is not one It is not one of the four simple sugars. So I'm just randomly generating a monosaccharide here. That bond doesn't want to become a bond. How on earth do you name a sugar for which there is no simple common name? This clearly is not maltose, cellobiose, lactose, or sucrose. In such instances, you can follow the following rules. If the disaccharide possesses a monosaccharide unit with a hemiacetal, the unit is named with the hemiacetal as the root. So if I look at this molecule, I see right here, that is a full acetal. There are two oxygens, there's no OH, so it's no hemi, but there is an H here. And this guy has an OH, and this is a hemiacetal. So what I do is I name the hemiacetal end as the root sugar. So I'm going to open this guy up and figure out what that is. I'm going to do that over here. I'm going to convert that to a Fischer. Okay. So right is below. So the anomeric OH is on the right. OH on the right. OH on the right. The CH2OH is up. So I've got a D sugar. And so here we go. Very good. And now if I break this anomeric, did I miss one? I did. Hang on. Whoa, 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 whoa. Let's not jump the gun here. I missed something. I missed one. Okay, so this guy is that guy. This guy is that guy. This guy is that guy. I missed this. Oxygen. That's an OH on the right. And then I have my cyclization. Okay, there we go. Now, this is my anomeric carbon, so I'm going to break this bond. Bring this down here to make the OH. And that OH becomes a C double bond O aldehyde. And so that fragment is this hexose sugar. Do you remember the name of that sugar? That sugar is D-allose. Okay. Now, the first rule simply said that that fragment that has the hemiacetal is named as the root or parent chain. And so when it's in ring form, it's an allopyranose, and the OH is down, so it's alpha. So I have, from that fragment, an alpha D allopyranose. So my first rule was to use the hemiacetal as the root name. The next rule states that the substituent with the full acetal, that's this section, that substituent, with the full acetal keto linkage to the previous parent is named by dropping the E and adding YL. The substituent name is placed in brackets. So that's part of it. So what we're going to do is we're going to figure out what sugar that is. So I'm going to draw the Fischer down here. So this OH is above, so it's, the anomeric OH is down, so it's to the right. And then we've got two OHs above, so they're to the left. This OH is right, because it's below. And we have a D sugar, so CH2OH is up, so there's my linkage. And down here we have CH2OH. Now as before, if I break the anomeric carbon, that becomes an aldehyde. And this cyclized oxygen becomes my OH down here. And lo and behold, when I'm done that and I identify the sugar, I see I have a D-mannose. Now that I know I've got a D-mannose, I look to see if the oxygen at the anomeric carbon is up or down. The oxygen is down in the anomeric carbon. In a D sugar, anomeric carbon OH down means alpha. So that's an alpha D mannopyranose. But the rule stated drop the E and add YL. So this becomes an alpha D mannopyrano. I'm going to run over them. Okay, we're going to rub some of this out. We're going to move this allopyranose down. Because I'm squeezing this together too much. Give me some room. Alpha D mannopyranose becomes alpha D mannopyranosyl. Drop the E of the O's, and it says put it in brackets. And then we have an alpha D allopyranose. Now, I have to tell you exactly where this alpha D mannopyranosyl is attached. Rule 2 states that the substituent name is placed in brackets and the position of substitution of the parent chain is indicated by a number from the number of carbons distant from the anomeric carbon of the parent root, and if it's attached to oxygen, this number is followed by a hyphen and a capital O. So if I come along on the root, which is allopyranose, and I number from the anomeric carbon, well, that's 1, 2, 3, 4. He's attached at the 4th oxygen of the allopyranose. So I would put in front of this 4 hyphen O hyphen. So this is a 4O alpha D mannopyranosyl alpha D allopyranose. Now, if you're given this name, you can easily draw this structure by going in reverse. You need to figure out what allose and mannose are, so you draw their structures on scrap paper. Then you would cyclize them, and you'd make alpha D, so I'd convert this guy to this. And remember, in the Fisher, the alpha means on the same side as the reference, and the reference oxygen is the one being cyclized. So the new anomeric OH points there. And then I'd use this to generate my alpha D mannopyranose. Using my rules, right is below, left is above. Right is below, that's from the anomeric. Left is above. Left is above. Right is below. And so there is my alpha D mannopyranose, and I'd link that in. So that guy you see is this one. And I'd do the same thing for D-allose. I'm not going to do it here. And then I would bring my 2 fragments and hook them up through an alpha 1,4 linkage. And I know it's alpha because I have the alpha D mannopyranosyl. And for it to be alpha, in allose, the O is down, so the 2 must link up. And perhaps I should show that. Okay. So let's do that. So let's rub out this name. So I now know I've got this mannose fragments. That's my mannose fragment I have to use to build the sugar. I'm going to leave that sugar strong. Now I have to do the same thing with allose. So I take allose and I cyclize it. So here we go. And it's alpha, so the OH from the anomeric carbon forms on the same side as the reference. Now I construct it in a Haworth. And I make OH right as below, right as below, right as below, right as below again as a D sugar. So now if I place them in proper order, I know because allose was in the root name, this will come on the right, and I've got to put my mannose over here. Because his name was in brackets. Now, how do I link them? I've got two separate sugars drawn on scrap paper. How do I make my final structure? Well, you see, to be alpha mannose, I've got to have the OH down here, so that OH is down. To hook to the fourth oxygen to be allose must be down as well. So that means this guy's down and that's down. And lo and behold, I've been able to draw the disaccharide from the name. Well, what about the case for the situation where you don't have a hemiacetal, such as we had in sucrose? Let's redraw sucrose. And try naming it according to rules 1 and 2 and see what happens. Just put that OH like that. So here we go with sucrose. How do we name something like this? And we have a problem, a deficiency in our two rules for naming. Rule number 1 stated that the root or parent was the one with the hemiacetal, and hemiacetals are named as sugars. But there is no hemiacetal or hemiketal. There's only full acetal ketals. And so we need a third rule in which to derive a nomenclature for this. In some disaccharides, there is no hemiacetal anomeric carbon. But all anomeric carbons are tied up in full acetal, full ketal, or full acetal ketal ends. In this case, the highest priority monosaccharide by functional group is taken as the root and given the oside ending. Aldehydes are higher priority than ketones, so aldoses are higher priority than ketoses. Substituent is named by dropping the E and adding YL. The substituent is separated from the root by a space and no brackets are used. Okay, so if you remember, sugars that had a carbon attached here, like this, were named as glycosides. This is a glycoside. And the way you named this was, if we had an OH here, this would be an alpha D glucopyranose. But because there's no OH, because there's a methyl, we have an alpha D glucopyranoside, and we bring the alkyl group out front as a methyl. Well, we name the disaccharide alpha D glucopyranoside in much the same way. In this case, however, because the aldose was made from an aldehyde, we're going to use it as the root. And since the O is down, again we have an alpha D glucopyranoside. Because note what's attached to the oxygen of the D-glucopyranose. It's a carbon. This is a big carbon molecule, but it's a carbon. So this is a glycoside. Now we have to name the substituent out front as an alkyl. Well, what is that substituent? Well, that substituent is a beta-D-fructofuranose. Well, we don't say methane. We dropped the ane and added YL. We're going to drop the E and add YL. We're going to put beta D fructofuranocil. So sucrose could also be called, make my D a little better, beta D fructofuranocil space alpha D glucopyranoside. Notice the glycoside methodology of naming is only used when you have no hemiacetal at any anomeric carbon in the disaccharide. Okay, the last thing we want to discuss about disaccharides is how they can be broken down enzymatically. Enzymatic hydrolysis enzymatic hydrolysis of disaccharides. Now, this can be a little confusing, so we want to take some time and look at it. First off, one should know that enzymes hydrolyze specific glycosidic linkages. Maltose, for example, can be broken down or hydrolyzed by an enzyme called maltase. Maltase is an enzyme that specifically cleaves alpha glycosidic linkages. So it cleaves alpha glycosidic linkages. Because of this, maltase is often called an alpha glucosidase. Okay. Cellobiose, on the other hand, can be cleaved by an enzyme called emulsin. And you can guess what it cleaves. It cleaves beta-glycosidic linkages. Beta-glycosidic linkages. And it's referred to as a beta-glucosidase. Now, do you remember what glycosidic means? A glucosidase, when you say something is an alpha-glucosidase, you're saying it breaks down alpha-glucose linkages. If I said something was an alpha-glycosidase, I would be saying it breaks alpha-carbohydrate linkages. One is more specific than the other. Saying something breaks alpha-carbohydrate linkages is only saying it will break any alpha linkage in a carbohydrate. But if I say something's an alpha-glucosidase, I'm saying it breaks alpha-glucose linkages. Right? Now, lactose can be cleaved by an enzyme referred to beta-glycosidase lactose. Beta-glycosidase lactose. Okay. Now, what kind of linkage is in lactose? Lactose has a beta 1,4 linkage from a galactose. So this must be a beta-galactosidase because it's breaking down a beta-galactose linkage. Right. Let's see if we can create a flow chart that summarizes these enzymes that break disaccharide linkages. Right at the top, we'd have the term glycosidase. Remember, glyco is the prefix that simply means carbohydrate. Glycosidase, therefore, is an enzyme that breaks a carbohydrate linkage. Every enzyme that cleaves any kind of carbohydrate would fit in this category. Now, there are two types of carbohydrate linkages. There are the alphas, 1,4s, and the beta 1,4s. And hence, glycosidases are broken into two groups. All the enzymes that can break down the alpha linkages, and so these are the alpha glycosidases. And all those enzymes that can break down beta carbohydrate linkages and beta glycosidic linkages, and hence they would be called beta glycosidases. So when you say beta glycosidase, you're a little more specific than just saying glycosidase. You're saying, well, this enzyme only works on beta carbohydrate units. But you can get even more specific. When you use the term alpha glucosidase, you're saying the enzyme will break an alpha glucose linkage. I would not try to use an alpha glucosidase on an alpha galactose. Beta glycosidases can be subdivided into others, enzymes. Beta glucosidase, for example, would be far more specific than saying beta glycosidase. You may have beta glucosidase, or you may have a beta galactosidase. Now let's consider a reaction that would exemplify what I mean. I'm going to just draw a carbohydrate here that is a disaccharide. And I'm going to make this molecule. Of course, I'm going to make it one we've seen. And so I'm going to draw alpha lactose. Alpha lactose, remember, has a beta 1,4. So I better fix that, eh? A beta 1,4 linkage from a galactose to a glucose. And so what I've drawn here is alpha lactose. And now, over the arrow, I'm going to write an enzyme name. Now what I want you to do, is once I write the enzyme name, is tell me if it's going to give me no reaction, or whether it will cleave this molecule into a beta galactose and an alpha D, a beta galactopyranose and an alpha D glucopyranose. So let's start with glycosidase. What does that word mean? It means enzyme that cleaves carbohydrate. Is this a carbohydrate? The answer is yes. So if I just write glycosidase over the arrow, you may assume that I use an appropriate enzyme to cleave this molecule, because it is a glycosidic linkage. And so you would draw your two products. Okay, and I'm not going to draw them out. You can draw them separately, which would be your galactose with its beta linkage plus your glucose with its alpha linkage. Maybe I will draw it out if I can squeeze it in. And guess what? I made a glucose here. That should have been up. Okay, so glycosidase will give me this. What if I said beta glycosidase? Well, beta glycosidase cleaves beta linkages. What kind of linkage do we have here? Alpha lactose. And don't be thrown off by the name. I don't have to give you the structure. I could write the name alpha lactose. Alpha lactose has a beta 1,4 linkage. Alpha lactose will be cleaved by a beta glycosidase. So again, you draw the same products. What if I said alpha glycosidase? Alpha glycosidases cleave alpha glycosidic linkages. Alpha lactose has a beta linkage. Look at this linkage right here. That is a beta 1,4 linkage. It's not alpha. And so it is cleaved by beta glycosidase. It's not alpha. So if I wrote alpha glycosidase, the correct answer would be no reaction. What if I wrote beta glucosidase? Beta glucosidase. Well, the linkage beta 1,4, but what is this molecule? Which the beta linkage is from? What is that? That's a galactose. Beta-glucosidases cleave beta-glucose linkages. The answer would be no reaction again. If I said beta-galactosidase, then I would give the two products. Now also along with these comes the names emulsin, okay, maltase, and beta-glycosidase lactose. So watch for the disaccharide and the appropriate name of an enzyme. Make sure you understand the flow chart and understand how we're becoming more specific from glycosidase to alpha glycosidase, beta glycosidase, how we can become more specific, even more specific as to what the enzyme actually does. And watch for what's written over the arrow. Okay. Well, that's it for disaccharide chemistry. Next Scribblecast lecture, we're going to look at the polysaccharides. This is my Scribblecast lecture. I'm Dr. Brian Lloyd. Thank you very much.